Today we will start with new configurations for amplifiers. The configuration or two configurations that we have seen so far were common source for MOSFET and common emitter for BJT, with a small variation where we added a resistor between the source and ground in the case of MOSFET, or a resistor between emitter and ground in the case of BJT. But in the two cases, we had the input at the gate for MOSFET and output at drain. That's the common source amplifier. And for the BJT, we had the input at the base and the output at the collector. These are very popular configurations, very powerful configurations. But there are other configurations that correspond to applying the input and taking the output from other terminals. And we'll start today with the common gate amplifier, where the input is applied at the source terminal of the MOSFET, and the output is taken from the drain. And the gate is common. The gate has a pure DC voltage, which means that it's at signal ground. So the input is at the source, between the source and ground. This G is signal ground. And the output is at the drain, from drain to ground, and the gate is at signal ground. So the gate is common between the input and the output, and we call this common gate. All right, so in common gate, the input is at the source of the MOSFET, the output is taken from the drain, and the gate is grounded and is common. So we want to see if we have such a configuration, what do we get? Do we get good amplifier characteristics? What is the performance? And also we will do the same for the BJT, where we will call the configuration a common base. The input will be at the emitter and the output will be taken from the collector. So that's my signal source here, VSIG, RSIG, or just RS. The input is here at the source. So VI is between S and ground. And the output is at the drain. Of course, the MOSFET should be biased in the saturation region, should be ready to amplify. And the way we bias it, we make sure that it has large DC VGS and large DC VDS. So V bias here, this voltage and this DC current source, they set the proper bias conditions so that the MOSFET is in saturation. Okay, so this is the configuration, and we're showing that we have a load RL. In general, we will have a load RL. And this RL can also be used to model the output resistance of this in case it's not ideal. If this has an output resistance, this can go and become part of RL. So RL is a convenient model for a load or the output resistance of the current source. So let's see what would the small signal model look like. We'll start at low frequency, and we'll start with the simplifying assumption that there is no small RO for the MOSFET. So at low frequency, I wouldn't worry about the capacitors, CGS, CGD, and CDB, and others. And also, I will not include for now small RO. So that's my MOSFET here: gate, drain, source. That's my input. The input is connected to the source. That's my output taken from the drain. The current source that was here disappeared because it's pure DC current, becomes an open circuit. The gate, we show that it's grounded because it's at a pure DC voltage V bias. So that's 0-volt signal. So ground. And this is the T model of, the hybrid pi model, the small signal model of the MOSFET. VGS between gate and source, and then GM-VGS flowing from drain to source. So that's the low frequency model without the RO. If you look at VI and VGS, VI is between the source of the MOSFET and ground. VGS is between the gate of the MOSFET and the source of the MOSFET. But the gate of the MOSFET is grounded. So this means that VGS is minus VI because the gate is grounded here. And this means that this controlled current source, GM-VGS, can be replaced by a controlled current source equal to minus GM-VI, which is a controlled current source equal to GM-VI, but flowing up. So if I change the direction of the current to upwards, I can change the control source to GM-VI instead of GM-VGS flowing down. And now I can redraw the circuit to make it simpler. Actually, it's a very simple circuit once we redraw it. It looks something like this. So V sig R sig, and the input is at the source. There is a GM-VGS from drain to source, which is equal to a GM-VI from source to drain. And then the output is taken from the drain to ground. That's it. So let's start with the input resistance. We want to find the characteristics of the amplifier: input resistance, output resistance, and open circuit voltage gain. Input resistance is VI over II. So this input current is obviously flowing. There's a single loop in this circuit, so this current is flowing like this, and therefore must be equal to GM-VI. The input current II must be GM-VI. And we know that the definition of input resistance, Ri, is VI over II, so 1 over GM. So the input resistance in this case is 1 over GM. GM for a MOSFET is, say, around 1 milliamp per volt. So the input resistance here is around 1K, in the range of kilo ohms. And for a MOSFET, this may be a bit surprising because we're used to having an infinite input resistance at the gate. Now here, when the input is applied to the source, we're talking about a small input resistance relative to the very, very large, almost infinite input resistance when the input is at the gate. So that's the first interesting result, kind of surprising. This amplifier can have a small input resistance. And here, because the input current is not zero, let's look at the current gain. What is the output current divided by the input current? This is a quantity that we did not calculate before for the common source because it was infinite. When the input current is zero, whatever output current I have, the current gain would be infinite. But now there is an input current, there's some II, which is not zero. And also there is an output current, and the output current, in fact, is equal to the input current because this II continues and flows in RL and becomes IO. So this input current is exactly equal to the output current. And this current gain for this amplifier, IO over II, would be 1. The output current is equal to the input current. We can easily find the voltage gain, actually, because VO, the output, is RLII, and VI is RIII. So VO over VI would be RL over RI, and that's GMRL. So that can be a large gain, and the expression here is similar to the expression of the common source, except that there's no minus sign. So the magnitude is comparable to common source, but there's no inversion. So if VSIG here starts going positive at t equals 0, the output will also start going positive, no inversion, but much bigger. The gain is GMRL, so the output will be GMRL times bigger than the input. This should be here at the input, not at VSIG. If I want to find VO over VSIG, then I have to modify this. So let me erase this here. So that's the input, resistance, current gain, and voltage gain. And now let's see what is the output resistance. Output resistance, I'll simply use the definition, set the input to 0. So VI here becomes 0 here. So it's like saying short the input and connect a test source, V test, and find I test, and take the ratio. So V test, I test, that's, we're interested in the current I test when the test source replaces the load RL and the input is set to 0. But if the input is set to 0, this means that this now is 0. So minus I test, which is GMVI, is 0. So I test is also 0. So there's no current flowing out of the test source. And this means that the output resistance is infinite. So this amplifier has an infinite output resistance, and we said previously that it has a relatively small input resistance. So small input resistance, large output resistance, current gain equal to 1. These are interesting characteristics. And if we want to make use of such a configuration with such characteristics, this can be used as what we call a current buffer. A current buffer is a circuit that has a small input resistance, a large output resistance, and a unity or almost unity current gain. So this has some uses as I just mentioned, as a current buffer. Now we ignored RO, but RO actually has an important effect here. Before we look at the effect of RO, let's come up with not a solid rule, a rule that applies only if RO is not considered or very, very, very large. And the rule is, if you're looking into the MOSFET source with the gate at some DC level, so the gate is at signal ground, and if RO is very, very large, then the resistance seen looking into the MOSFET source would be equal to 1 over GM. This is the result of the previous slide when we calculated the input resistance. I was looking into the source of the MOSFET with DC at the gate and no RO. So here's a MOSFET with some DC voltage here and no RO. So this is kind of important in this case. So if there's no RO and I'm looking into the source, so here's the eye that measures the resistances seen at the node. What would the eye see? If there is a DC here and RO is very large, it will see 1 over GM. The resistance seen looking into the source will be 1 over GM. Again, this is one of the rules that we will have, but we will modify it, because if there is an RO, the error will become quite large if I use this. So let's consider now the case when RO is not neglected, RO is not very, very large. So here's the same configuration now with RO. So RO is now between drain and source, where it should be. And the rest of the circuit is still the same. So this is my input at the source. This is the input current. And this is my output current. And the MOSFET GMVGS would be minus GMVI, because VGS is minus VI. And we added RO. So let's see what happens to, say, the input resistance in this case. Well, of course, it will be VI over II, but now II is no longer equal to GMVI only. This is the input current, and it will split in two. So it will be this plus this. So GMVI plus the current in RO. The current in RO is the voltage across RO divided by RO. This current will be the voltage VRO over RO. What's VRO? The voltage here is VI. The voltage here is VO. So VI minus VO over RO. That's the input current, GMVI, plus VI minus VO over RO. Okay, what's VO? Well, this current then, these two currents will then join, and the sum will be the output current, and it will be back to II. So II splits in two, and then the two join, and they return to their sum, which is II. So VO, therefore, which is IORL, would be IIRL. The current gain is still 1. So VO is RLIO, which is equal to II. I'll take this and put it here. And I get now an expression for the input current, which is II equals GMVI plus VI over RO minus RL over ROII. I take the II to the other side and simplify to get the input resistance in this case, which is RO plus RL over 1 plus GMRO. So this is what happens when RO is considered and not very, very large. This is the expression for the input resistance in this case, and it is interesting in two aspects. The first is, let us see if it reduces to 1 over GM, which we derived on the previous slides, if RO is very large. So let's see, if RO is very large, would this be 1 over GM? If RO is very large, so the limit as this goes to infinity and this goes to infinity would be infinity over infinity. Okay, that doesn't help a lot. Maybe we can use some techniques from calculus, L'Hopital rule or something like that. So this will be 1 over, right? So take the derivative of this with respect to RO, 1. Take the derivative of this, GM. Oh, perfect. So that's 1 over GM as RO goes to infinity. And that's consistent with the previous result. All right. The second thing is, even though we said on the previous slides that this is kind of a small resistance when it's 1 over GM, in fact, it can be large. Because if RL is very, very large and RO is large, even though GMRO is also a large number, but if RL is very large, that can be large. So that's when we say that the input resistance is small, this is true if RO is very, very large. That's a bit confusing here. But say RL is of the order of, say RL is of the order of like GMRO and times some factor. And we have and as RL goes to infinity, say, what happens to this? Actually, this input resistance, which we said would be small, if RL goes to infinity and RO is some, say, 50K, 100K, and this is 30, 40, the whole thing would go to infinity. And therefore, the input resistance can become quite large. And the statement we said that the input resistance of common gate is relatively small will no longer be accurate. The input resistance is small for a common gate only when RO is very, very large. If the RO is considered and RL is very, very large, so as RL goes to infinity, the input resistance would go to infinity also. Oh, there's one more thing. Why did I start using RN, RIN instead of just RI? I don't know if you noticed that we added N. So far we used just RI. And this is because this is the expression that we're getting for input resistance, and it includes RL. The input resistance is now dependent on the load. So from now on, whenever I have an input resistance for an amplifier that depends on the load, I will add N to RI and call it RIN. So it's still VI over II, and everything is still the same, really. It's called input resistance, and it's input voltage divided by input current. But it's only just to remind myself that this particular input resistance depends on the load. So why am I reminding myself of that? Because in the amplifier models, when we try to model an amplifier, and there is a load connected here at the output and a source connected here, the model for the amplifier assumes that the input resistance here inside the amplifier, the output resistance, and the open circuit voltage gain, all of them don't depend on what's connected to the amplifier. So to find the input resistance, output resistance, and AVO, and open circuit voltage gain, you just look at the inside of the amplifier. So inside the amplifier, you'll have MOSFETs, and the MOSFETs would determine MOSFETs and resistors, and the MOSFETs and the resistor will determine the input resistance, output resistance, and open circuit voltage gain. This is the first time where the input resistance not only depends on what's inside the amplifier, but also on what's connected at the output of the amplifier. So that's why we add the letter N to just remind ourselves that this Rn, in this case, also depends on RL and not just on the amplifier that I'm using. So if I change the load, the input resistance changes. So we emphasize this fact that the input resistance for this amplifier depends on RL. So that's input resistance. Let's find the other quantities of interest like AVO, open circuit voltage gain. And that's something that we find by finding VO over VI when there is no RL, open circuit voltage gain. AVO is VO over VI when you open circuit RL. So here, there's no RL, we open circuit RL. And I want to find VO over VI. So this current GMVI now cannot flow like this. No current can flow like this now. There's no output current. This is 0. And therefore, the GMVI current will have to circulate back. So this current circulates back in RO. And that's how I can find now VO. Because RL goes to infinity, there's no current in the load. And VO will be VI by KVL plus GMVI RO. So the voltage here plus minus would be this voltage plus this voltage. So the voltage across RO, which is the current in RO times RO. So GMVI RO plus the voltage VI from here to here. So VI plus GMVI RO. And that gives me a nice expression for AVO. 1 plus GM RO. So here you see that the value of AVO depends on the inside of the amplifier. That's the GM of the MOSFET and the RO of the MOSFET. That's AVO. If I want to find the voltage gain, I can use this AVO and say that the voltage gain is AVO times RL when I connect a load divided by RL plus the output resistance RO. But I don't know yet the output resistance. So that's, if I know the output resistance, I can use this and find AV. Or I can connect a load and find AV. So if I connect a load and find AV, the circuit will become like this with an RL. And it's not too complicated to analyze, quite easy to analyze. The load, the output current here is equal to the input current. So VO is IIRL. And the input current is VI over Rn. So VO over VI is, this is the voltage gain, RL over Rn. And I have an expression for Rn from the previous slide. And if you take this expression and simplify it, you get AVO times RL over RL plus RO. And you will get a small RO here. So this is like a hint that the output resistance is equal to small RO. Well, we can show that it is very easily. So let's do the output resistance for our common gate. Output resistance with VI equal to 0. We set the input to 0 at the source. So that's the 0 at the source. Disconnect the load, connect a test source, Vx, Ix, and find Ix. Well, if VI is 0, this is 0. There's no current here. So what do you have left? Just RO. And this is the output resistance. So that's very easy to show. So now I know that AV would be AVO, RL over RL plus small RO. And that this was 1 plus GM RO, RL over RL plus small RO. Let's introduce a new quantity now, R out. So what is this R out? This is the output resistance when Vsig is 0. So this is not really the amplifier output resistance. This is just a quantity that looks like output resistance because we find it by looking at the output after disconnecting the load. So it's not the output resistance of the amplifier, but in many cases, we need to find such a quantity. For example, when we're doing OCTC. So to, again, differentiate between the output resistance, the regular output resistance of the amplifier, we will use RO for output resistance. This is the regular output resistance of the amplifier with VI equal to 0. And this one, we will call it R out. And this is when we set Vsig equal to 0, not VI equal to 0. Again, this is not the amplifier output resistance. This is a quantity that often you would like to know. So in this case, in the case of the common gate, if I want to find R out, I set Vsig equal to 0, not VI. So now I have Rs. This is the input. And this is the output. Disconnect the load, connect a test source, and find the resistance seen by the test source, which is Vx over Ix. Now, Vi is no longer 0 because Ix continues here. So there is a potential drop across Rs, which is Ix times Rs, and that's equal to Vi. But if you look carefully at the circuit, we have a rule for this. We are looking into the drain of the MOSFET with RS between the source and ground. So this is the resistance seen looking into the drain with DC at the gate and RS between S and ground. And we know what this is. This is the RXY. R out is therefore RO plus RS plus GM RS. The output resistance of the common gate is small RO only. But this quantity R out, which sometimes we want to find, we set Vsig equal to 0 to find it, is small RO plus RS plus GM RS, because we're looking into the drain of the MOSFET with DC at the gate, a certain bias voltage at the gate, and between the source and ground, I have RS or Rsig. Here's the same circuit at high frequency with no RO. If I add the capacitors, I will have two capacitors in this case. I will have a Cin here between the input and ground at the source, and a C out. And unlike the common source, there's no capacitor that bridges the input to the output. Cin is the CGS plus CSB if S and B are not connected together. And C out is CGD plus CDB plus any CL, any load capacitance. All right, so I have two capacitors, Cin and C out. One is at the input and one is at the output. I can apply various methods. One method is to find the transfer function of the circuit. So by writing two node equations, we get two RC circuits, one at the input and one at the output. So at the input, Vs, which is equal to Vn, this is the input. The input voltage divided by Vsig is this, which can be written as K over 1 plus S over omega at the input. And with the output divided by the input, Vo over Vs is another K divided by 1 plus S over omega out. So the overall transfer function looks like Am divided by 1 plus S over omega P1 times 1 plus S over omega P2, where Am is the AV that we calculated at low frequency. Omega P1 and omega P2, we can find them from here and here. So omega P1 is 1 over Cn into Rs parallel 1 over Gm, and omega P2 is 1 over C out RL. Now we can use any method we like. If one of the frequencies, if one of the poles is dominant, then omega H would be that. Or we can use the square root function, or we can solve exactly, it's a simple transfer function, just two poles, no zero. Now, of course, we neglected our O here. And what if we want to consider it? If we want to consider our O, the transfer function may not be as easy to derive. But what we can do is we can apply OCTC. So I have the two capacitors, and I will find the resistance seen by Cn, and then the resistance seen by C out. So the resistance seen by Cn, let me go back, and let's find the resistance seen by Cn. In OCTC, if I want the resistance seen by Cn, so this is Cn, now I'll have a test source here, and I will have Rs. I set all the sources to 0, so V sig becomes a short. That's RS. And from the other side, I have the MOSFET GMVI with RO and RL. And C out is open circuited. So I want to find the resistance seen by Cn. To find the resistance seen by Cn, I look left, and what do I see? I see just RS. I look right, and what do I see? If I look right at this terminal, I will see the input resistance of the common gate amplifier. This one, we called it Rn. So instead of doing a full circuit analysis, I'll just combine the two resistors RS and the resistance Rn. And Cn will see their parallel combination because they're both connected from the same node to ground. For C out, I open circuit Cn and set V sig to 0. So this is V sig, RS. Now Cn is an open circuit, RO, GMVI, RL. And this calculation of the resistance seen by C out, RL stays in OCTC. There's nothing that says that you disconnect the load. So when you want to find the resistance seen by C out, which is here, this is C out, RL is still connected. So the resistance seen by C out would be this RL in parallel with whatever I see looking back into the drain of the MOSFET with RS connected and V sig equals 0. And this is what we just called this R out. And therefore the resistance seen by C out would be R out in parallel with RL. And I have expressions for Rn and R out, and then I combine them, Rn with RS, R out with RL in parallel. And these are the resistances seen by Cn and C out. And of course, omega H would be approximately 1 over the sum of the time constants. So 1 over Cn times Rs parallel Rn plus C out R out parallel RL.